So what we're going to do is we're going to have a look at the ladder problem, which is a torque issue through static equilibrium. We're going to have a couple things to deal with. First of all, reading the problem, it says a firefighter stands 2/3 of the distance up a 4-meter long ladder with a mass of 35 kilograms that is leaning up on a burning house. Assume that the friction between the ladder and the side of the house is negligible. Just describe that as mu2 equals 0. And we'll talk about mu1 down here. The total mass of the firefighter in the gear is 95 kilograms. The ladder makes an angle with the horizontal, which is 58 degrees. What must the coefficient of static friction between the ladder and the ground, again, we're going to call that mu1, be to prevent the ladder from sliding backwards? So we have a ladder, it's up against the house. We want to make sure that the ladder doesn't slide out this way. So we have a couple things to do. First of all, we're going to have to put the forces on it. We'll put the obvious ones on first. So first of all, we have obviously the weight of the firefighter, which I'm going to signify by WFF, or weight of firefighter. The ladder has a mass, which is 35 kilograms. So somewhere is in the midpoint here at 1/2 the length. We have the weight of the ladder. Now, this ladder is pushing down on the ground, so Newton's third law says that every action has an equal and opposite reaction, so it's also not moving. So we know that the ground is pushing back up, which we're going to call normal ground. We know that if the ladder is leaning up against the house, that we are going to have another normal force of the house pushing back, which we're going to call normal house, or NH. And finally, we have a force of friction, which is going to stop the ladder from sliding out backwards. Now, the weight of the ladder and the weight of the firefighter are fairly trivial because we have their masses. The normal force on the base of the ladder is also pretty simple because we know that the ladder is not sliding up or down, so it must be balanced out with whatever these two forces are, because the other two forces are going along the horizontal. So we know that the normal force of the ground will be equal to the sum of those two forces. We know that there are only two forces in the horizontal direction, the force of friction and the normal force from the house. So they're going to be equal and opposite because hopefully the ladder again is not moving. So our goal here is to find mu1, and that's going to be equal to the force of friction divided by the normal force of the ground. So when we see this, zoom out here for a second, when we see this, what we need to be able to do is figure out what FF is. And in order to do that, we don't have the force of friction and we don't have the normal force from the house, so we have to solve for one of them. And we're going to solve for the normal force of the house using torque. The normal force of the ground, we don't need torque to solve for because we have all of the information except for NG that we need. So we'll start just by solving what we can right off the bat. We know that in static equilibrium, the sum of the forces in the vertical direction are equal to 0. And that's going to be equal to the normal force of the ground minus the weight of the ladder minus the weight of the firefighter. Let's just slide this back over. So the normal force of the ground is equal to the weight of the ladder plus the weight of the firefighter after you rearrange it and get my vector signs in there. So the normal force on the ground is equal to the mass of the ladder times acceleration due to gravity plus the mass of the firefighter times acceleration due to gravity. So let's start throwing some things into this. 35 kilograms is the ladder, 9.81 meters per second squared is the acceleration due to gravity. The mass of the firefighter and their gear is 95 kilograms times 9.81 meters per second squared. So we have that all solved out. Throw it into the calculator, and we find that it is 1275.3 newtons. So we can kind of knock that one off. We've got that vector. And we come back over and we look at the normal force due to the ground. That has already been solved now. So now we need the force of friction. In order to get the force of friction, we have to solve for this. So what we're going to rely on is that the sum of the torques are equal to 0. So the sum of the torques on the system must be equal to 0. Now, we have to pick a pivot point for a torque problem. It makes sense to pick this one down here where the ladder meets the ground because we have two forces acting through it. And because torque is force times distance, or perpendicular distance, these forces are acting right on the pivot, so their distance is 0, and neither of them will factor into our calculation. So we don't need to know force of friction if we apply the pivot here. So for my problem, I'm going to assume that counterclockwise is positive. Sorry, clockwise is positive and counterclockwise is negative, just to make my life a little bit easier. So the torque due normal to the ground will be negative because it's going, it would make it rotate up that way. Even though it's at 0, we're going to include them all right now. So plus the torque due to the ladder, plus the torque due to the weight of the firefighter, minus the torque normal from the house. Whatever convention you use, it will give you the correct answer no matter what you do. So we only have to worry about the torque because of the ladder, the torque because of the firefighter, and the torque because of the house. Those two don't matter, so we're down to 3 forces. I have everything I need for these 2 forces, or these 2 torques. And the only thing I don't have is the normal force of the house. So rewriting it, I have 0 equals the torque due to the weight of the ladder plus the torque due to the weight of the firefighter minus the torque normal house. We simply expand it. So the weight of the ladder will be the mass of the ladder times G times. So I need to know not just what the distance is on the ladder, I need to know the perpendicular distance, or what we call the moment arm. So I'm going to write distance perpendicular ladder for this. And we're going to come back and we're going to go and solve what that is and discuss how we know. So the weight of the firefighter will be the mass of the firefighter times gravity times the perpendicular action of the firefighter minus the normal force of the house times the perpendicular distance of the house. So we have a lot of information, but we can't just use these distances. We know that the ladder itself is 4 meters long, but the problem is torque is a perpendicular. The torque is generated by a perpendicular force on the lever. So we have to sort of figure out what we're going to do about that. So we're going to just switch over and we're going to look at the perpendicular force of the ladder. I'm just going to switch over to a blue marker so we can have a look, a little more detail of that. So here's the ladder. And to determine where you're going to get this perpendicular force, you extend your force down with a little dot. I use a dotted line. which we call with a little dotted line that's straight down. Probably should use a ruler, but straight down, and we call that the line of action. From the pivot point, you extend this over. It is the distance between here and here that we call the perpendicular distance of the ladder. Now we clearly have a right angle triangle here. I know that the distance from here up to here is 1/2 of the length of the ladder, 1/2 L, or 2 meters if we're just going to go out and solve it. So in order for me to do that, I need to figure out what trig function to use. So I have the angle at 58 degrees in here. I have the hypotenuse at 1/2 L, or 2 meters. So I'm looking for the adjacent side. So I'm going to use cosine. Now we remember that the cosine of an angle is equal to the adjacent side over the hypotenuse. I have the hypotenuse, I have the angle, so the adjacent side can be solved by the cosine of that angle multiplied by the hypotenuse. Now we're not going to, when we talk about the adjacent side, we're talking about the perpendicular side, and for the hypotenuse, we're talking about 1/2 L, so cos theta times 1/2 L will give me my value. So cos theta times 1/2 L. I'm going to leave a line, and then we'll solve each one separately. So I'm going to switch colors again. I need to get the perpendicular force of the firefighter. So I'll do the same thing. I'll extend the line of action down, and then across the bottom, I'll get the moment arm, or the perpendicular radius. Once again, it will be the adjacent side. So our perpendicular firefighter is equal to the cosine of the angle times if you read the problem, he is 2/3 of the way up. So 2/3 L. And finally, the next one's a little bit more difficult, and I have a lot of mess over here, so it's going to be a little bit harder to see. But we do exactly the same thing, but here's the normal force of the house. So we're looking for the perpendicular force of the moment arm caused by the house. So we extend the force outward, and we take up from the pivot point. I'm going to go through some of my writing here. We get so there's our line of action, and there's the moment arm. So this is the perpendicular one we're talking about. So our perpendicular, did I call it just with an H? Our perpendicular with the house. Now, if this angle in here is 58 degrees, this is 58 degrees. So now we're looking for the opposite side. So that's going to be sine theta is equal to opposite over hypotenuse. We have the hypotenuse still, it is just L. And we can solve the moment arm that way. So our perpendicular house is equal to the sine of the angle times L. My green does not show up well, so I'll just go over it in black. Now we can just sort of plug along and solve for these moment arms. So the cosine of 58 degrees times 1/2 times 4 meters is 1.06 meters. The moment arm of the firefighter is the cosine of 58 degrees times 2/3 times 4 meters, and that one is equal to 1.41 meters. Finally, we have the one that's slightly different. It's just the sine of the angle, the sine of 58 degrees. times 4 meters, because the hypotenuse is the whole ladder, so it's L. And that's equal to 3.39 meters. So we have that all solved out. We can kind of slide down and start using those numbers and plugging in what we have. So 0 equals the mass of the ladder, 35 kilograms, times 9.81 meters per second squared, times the moment arm for the ladder, so I'm just going to go up and get that, 1.06 meters, plus the mass of the firefighter, the mass of the firefighter is 95 kilograms, times 9.81 meters per second squared, times the moment arm is 1.41 meters. Take away the normal force on the house times the moment arm for the house, which is 3.39 meters. I'm going to just close that off. So now we have the expression filled in, and we only have one variable, which is the normal force for the house. So let's just solve out for what we have here. 363.951 Newton meters plus 1314.05 Newton meters minus the normal force of the house times 3.39 meters. We'll combine those two and move the normal force and its distance across. So I get the normal force of the house times 3.39 meters is equal to 1,678.00 Newton meters. Divide both sides by 3.39 meters. That will give me 494.99 newtons is the value for the normal force acting on the house. So we have two values that we need. There's the normal force due to the ground. There's the normal force to the house. And we remember that we said the horizontal components, or the I-hat direction, the sum of those needs to equal 0. So that means that the force of friction plus the normal force of the house must equal 0. So it's not a big stretch to say the normal force is equal to the negative of the force of friction. So finally, we can solve this question because we know the coefficient of friction is equal to the force of friction divided by the normal force acting. So in our case, it's the force of friction, vectors on here, the normal force due to the ground. You just use absolute values because the direction is irrelevant for the coefficient. So the force of friction is 494.99 newtons. And the normal force for the ground is 1275.3 newtons. Mu is equal to 0.388 newtons. 0.388. Sorry, not newtons. So basically what we arrive at is, in this situation with the ladder, we need to make sure that we take into consideration the moment arm. That's probably the biggest trick with this. Then it's just a system of equations, essentially, where you're just solving all the pieces and coming down to the same term, and you end up with a coefficient of 3.388. If the coefficient of friction is higher than that, you're fine. If it's lower than that, when the fireman gets 2/3 of the way up, it will slip out. So these are acting right at a distance of 0. So both of those do not appear in this question.